Today we're talking about something different though. It's not really the physics principle that's important. It's a mathematical thing you need to be able to do. It is very likely on your exam that you will hear the phrase, how's it put? It's usually put very specifically. Create but do not solve a differential equation. That could be used to, and then there'll be something after that. Then part B, solve the differential equation. So that is incredibly common. And what's really important to understand is that they've broken it up. In the old exam, they would not have that part about create but do not solve. So they have clearly tried to separate it out. What's important to note is that it's worth more points to create and do not solve the differential equation than it is to solve it. However, it takes a lot more time to solve the differential equation than it does to create it. Now, a lot of you are going to think that this is calculus. It's not. It's differential equations. Differential equations uses calculus sometimes, and also uses a lot of other methods to solve differential equations. You are going to be taught a single method that is the most common. There's only 2, maybe 3 problems that they can possibly ask on the AP exam that have to do with differential equations. So they are all the same. Once you learn how to do this, all you really need to do is repeat it every week so that you are not scared of it and you know what to do. And any variation that crops up will cover every single one of them. So you will see this problem a lot every week. And I will force you to write all the steps out and submit it so I can see that you're writing them all out. And then at least once, I'm going to make you do it all right here in class to show me that you can do it. Does everybody understand? It's just too prescriptive not for you to do this, even though the actual math is pretty challenging. So today, I'm not going to use any calculus. I'm going to show you that they've already done the calculus for you. You just have to recognize it. But then later on, I'll show you how to do the calculus. So we are going to be talking today, the example we're going to be talking about is air resistance or air drag. And it's going to be based on a lab we're going to do sometime. I have to work it in. It doesn't fit in with anything that we are doing right now and won't for the rest of the year. So just sometime when we're between topics or we need a break, we're going to do the coffee filter lab, which is just dropping coffee filters. It's a pretty straightforward lab. When you drop a coffee filter through the air, the coffee filter will experience a downward force due to gravity. That's a big duh, and everybody knows that. However, the reason why we use a coffee filter is that the coffee filter is very light and has a large cross-sectional area compared to its weight. Because of that, air resistance can't be ignored. When the coffee filter is traveling slow, it will part the air as if it's passing through layers of air. We call this kind of air resistance laminar drag because the object is not significantly disturbing the layers of air. Now, if it's going fast enough, you will reach turbulent drag. Turbulent drag is when the layers themselves don't part naturally and you begin to get vortexes or air that's curled or air that's creating pockets of vacuum or pockets of high pressure. That's what happens when a plane reaches some kind of disturbed air. They call it turbulence, but a plane can create its own turbulence by disturbing the air. The lab itself, though, never has the coffee filter go so fast that it creates turbulence. That's going to always be in a form of drag called laminar drag. Now, the reason why that's important for me to explain is because laminar drag is a type of drag that is proportional to the velocity, meaning the drag force is equal to some constant times the velocity. Now, in 6th period, I made the constant a lowercase k. In this period, I made the constant a lowercase c. It doesn't matter what I use here. They switch it up all the time on the AP exam. Don't become accustomed to it. It just means that it's proportional to the velocity. The truth is, this is actually a collection of things that describe the coffee filter. Its shape, its cross-sectional area, its mass to area ratio, all of these things actually make a difference in what the value for C is. So things that are more aerodynamic will have a smaller value for C because you get less drag for your velocity. But something like a parachute, a parachute is specifically designed to have a very high value for C so that you get lots of drag. The coffee filter is pretty high. It's not particularly well shaped. So my Jeep, high value for C. A Prius, low value for C. I drive basically a Borg cube down the street. But something that's nice and aerodynamic, it cuts through the air cleanly. You guys have seen all the things they put on the trucks on the highway to make them appear to cut through the air a little bit cleanly. Little flaps they put on the back of the truck to try and allow the air to bend around the back of the truck more cleanly. If you haven't, just look at any of those big 18-wheelers. The stuff that's between the wheels that looks like pieces of metal, that's actually designed to create aerodynamic, less vortexes and more laminar flow of air around the trucks. They have lots of stuff trying to do that. Now, the drag force is against the direction of motion. So truthfully, I should put a minus sign here. But if I put the minus sign here, and in a few minutes, you'll see why I don't like to. Because the minus sign tells us the direction. And so I try to be careful about when I throw a minus sign in there. Drag is always against the direction of motion. But what that means is in my picture here, I'm just going to draw that as an upwards arrow and write CV. So nobody should ask me why I didn't make the CV negative now. I used a negative to indicate the direction of this force. Now, you guys might not be sophisticated enough to understand why I'm choosing this example, but I hope that you are. This is an interesting circumstance. I want you to consider what happens. When you first release the coffee filter, how fast is it going? What's that? 0. When I first release the coffee filter, at time 0, the drag force equals 0 because it's not moving. This is at t equals 0. Well, this clearly suggests that the coffee filter is experiencing an unbalanced force and will accelerate downwards due to the action of gravity. So, sometime later, just an instant or two later, the object, because it has accelerated, will still have the same weight downwards, but now will have a small force upwards representing the force of drag. Not much, but some. It's still accelerating downwards though, which means it's still getting faster. And because it's getting faster, the drag force is also getting faster. But it's still accelerating downwards. So it's still getting faster. And so the drag force will be getting faster. Now I can draw many of these little pictures, but what I'm going to do is skip to the end when it reaches what's called the steady state condition. Problems like this that have a dynamic force may sometimes reach a steady state condition, a condition in which the net force finally makes it to 0. There is a time when the velocity will grow great enough so that the drag force will be equal to the weight. At that moment, there'll be no change in the velocity. It will no longer accelerate. So at that moment, we're at a special condition called terminal velocity. And you can find out what the terminal velocity is without doing hardly any math. Right now, the terminal velocity occurs when the net force equals 0. If I haven't made that abundantly clear, you should put that in your notes. I think it's obvious, but a lot of students don't, and they get the first question wrong on one of these, which is, what is the terminal velocity? Well, it's when net force equals 0. It's when Vt equals mg over c. Net force equals 0. So those two things must be equal. Solve for the terminal velocity. Now, it might not be clear to you, but this is what skydivers are manipulating when they're changing their cross-sectional area. They spread out, they make c a bigger number, that reduces the terminal velocity, so they slow down. Somebody's beneath them and they want to catch them, they make their cross-sectional area smaller, that makes c smaller, that increases their terminal velocity, they speed up. They see the ground coming, they deploy their parachute. Make the C incredibly big to to reduce their terminal velocity to as small a value as possible to make sure when they hit the ground they don't hurt themselves. Good so far? Pretty obvious? So the problem that we will have then is what begins now. Create, but do not solve, a differential equation that could be used to find a function for the velocity of the coffee filter. What does this velocity look like? Now, I know what the answer looks like, but you don't. Could be anything. We know the velocity is going to increase, but it's going to increase and then reach some terminal speed where it will stop increasing. That's what we know. You've probably seen functions that do this before. What your job is to find what that function is and what parameters control it. Now, making a differential equation is not anything complicated. We've already done it. But because it's been a long time and I didn't always use the terminology correctly, I want to refresh your memory. A differential equation is just an equation that has a differential in it. That's all a differential equation is. But to create the appropriate differential equation that could be used to solve for something requires a little bit of thought. So the first thing I want to remind you is that you know about a couple of differentials. These aren't part of our steps or anything, but you have two differentials at your disposal, things we learned back in August. We know that acceleration and velocity can both be written as a differential, as the rate of change of something. So we know that velocity is dx dt, and acceleration is dv dt. Creating a differential equation is going to require that we do substitution. We want to introduce a differential into our equation. So we need an equation that either has velocity in it or has an acceleration in it. Now, to know where to start is important. So whenever you are asked to create a differential equation, there are only a couple of starting points. Starting point number 1 is Newton's second law. Starting point number 2 is conservation of energy. There are potential other starting points. I've never seen them asked on the exam. In fact, I can't remember the last time that conservation of energy was a starting point. We will do an example of conservation of energy as a starting point, but I can't remember the last time it was on the exam. The number one way to do this is Newton's second law. For what I hope is obvious reasons. It has acceleration built in. And because it has acceleration built in, it's the right place to go. But you still have to use net force. You have to use Newton's second law. So before you can create a differential equation, you need to choose whether net force is the best way to go or conservation of energy is the best way to go. This one should be obvious. We know about the forces acting on the object, so we're going to choose the route where we use net force. So your first problem is to do the net force problem. This one's not a hard problem. mg minus cv equals ma. There. We've done the net force problem. Now, to create a differential equation, we need to substitute in for either the velocity or the acceleration with its differential alternative. Now, choosing which one to go there, I think is a no-brainer, but it might not be for you. If we put in dx dt, we introduce x, but we still have the acceleration there. If we substitute in dv dt, if we substitute in dv dt, then we introduce v, and there's already a v in the equation. This reduces the number of variables in our function. And that's what we want to do. We want to introduce a differential that is related to a variable in the function. We want to introduce a differential that is related to a variable in the function. Now, that's hard, I think, for young students to recognize. There's a lot of variables there. M is a variable, G is a variable, C is a variable, V is a variable, and M is a variable, and A is a variable. It's a lot of variables. I count 5 of them. Which ones are actually changing, and which ones are staying the same? once I drop the coffee filter, do you understand that M, G, and C are all staying the same the whole time? So although they are variables in an equation, they're not changing. They are going to stay constant while the coffee filter falls. The true variables are the things that are changing while the coffee filter is moving, which really means that A and V are the variables of this equation. Now look, I understand that it all looks like alphabet soup. That's the part that's hard of this class, is recognizing the situation, what things are staying the same and what things are changing. And I'm understanding that I need to be more careful about that. But now that I've identified it, I want to substitute in a differential that matches one of the other variables. V is a variable that will be there if I substitute in dv dt for A. So that is the right thing to do. I am going to substitute in dv dt for the acceleration. And that's it. We have created a differential equation that could be used to solve for v as a function of t. Now, by the way, the problem definition told you which differential to use. Just so you know, when I said in the problem, create a differential equation that could be used to solve for velocity as a function of time, I was telling you to use that. If I wanted something that would solve for the position as a function of time, then I would use that. So I was telling you which one to use. But I want to make sure you understand you could figure it out for yourself. Okay. That's probably worth 2 to 3 points. Doing the Newton's law stuff and doing the sub in for your differential. But now, if part B says now solve it, that's some work. It's going to be some work now. But be aware, the modern exam doesn't want this to be all math. They want there to be physics. This is more physics, what we're doing here. Solving this is less physics. So they give points for recognition of the parts of this that are physics, and they give fewer parts that are pure math. There's a lot of pure math to do in this problem, a lot. Almost an embarrassing amount. But pay attention, I will tell you where you're going to get points. First things first, I'm a realist. You need to be careful here. If you're being asked to solve for v as a function of t, and you're going to begin the process, modern exams will show you what the answer is. They'll say, show that the solution of this function is, and they'll give you the answer. So you're not getting points for getting the answer. You're getting points for demonstrating certain mileposts. I want to make sure I highlight what those mileposts are, and I will do my best. But you have to start with a correct differential equation. Now, the process we're going to use, we've used before. It's more complicated in this circumstance, but we've used it before. We're going to use the process of splitting the derivative. That's what we're going to do. It's kind of a form of separation of variables, but splitting a derivative. It's not particularly hard to do, and there's a number of ways to do it. I like to solve for my differential first and then begin the process, but you don't have to. So I'm going to do this the way that I just suggested, which is to solve for my differential first. It's uglier though. So if you don't like the way the ugliness looks, then maybe not do it this way. But what I mean is I'm going to get the differential to be all by itself, which means dividing by m, you're getting g minus c over m times v. I've written this in such a way that I've collected the constants and left the variables separate. So that's why I wanted to do that. That's a collection of constants. Now, so again, step 1 is to solve for your differential. Step 2 is to split the differential. So splitting a differential is easy. You just want to separate dv and dt. They're a fraction. So that just means multiplying both sides by dt. But that is the next step, is to split this differential after you've solved for it. So I will multiply both sides by dt. People who have had calculus or are in calculus should begin to see that we are building an integrand. That's what's happening here. For you guys who have never had calculus before, just so you know, we are building an integrand. That's what's happening here. We're building something that we can integrate. But to do so, we have to be aware that we have function variables that are changing. So we have another step to do before we can actually get to the calculus. And that step is we need to collect like terms. This is different than an algebra version of this. It's a little more complicated. dv refers to small changes in v. It will be our integrating variable on the left side. And dt refers to small changes in t. It will be our integrating variable on the right side. We need to get anything that has a t in it on the right side and anything that has a v in it on the left side. And you will only be able to do this by multiplying or dividing. There's no way to add this to both sides. So this entire function will have to be moved to the left side because that's where dv is. And there is no reference to t, so there's nothing to move to the right side. All right, now we have done everything we can to get this in form for us to be able to integrate. And that's the next step. When you verify that you have your function variable on the same side as your integrand variable, and that you have, no other variable on that side that is changing as time changes, then you're ready to take the integral of both sides. Now, just drawing the integral symbol isn't taking the integral. But, and this is important, in the AP Physics exam, drawing the integral symbol is good for a point. They want to know that you know you have to integrate both sides. So usually a point is given for splitting the derivative and isolating the variables correctly. So this portion is worth a point. And this part is usually worth a point if you do the following step. Now, this is where I need to clarify. You guys are in BC. You learn something different than what you have to do in this class. The AP graders want something done a special way here. They want you to do a definite integral and not an indefinite integral. You won't lose points if you do it as an indefinite integral, but they specifically look for the definite integral. So for those of you who have no idea what I just said, ignore it. Ignore all of it. So you guys who have never done this before, what you have to do is you have to tell the integral where the starting velocity and starting time is and where the final velocity and final time is. You see, on an integral, a number goes here to represent the starting point, and a number goes here to represent the ending point. Yeah, okay. So, the important thing, and what the graders are looking for, is for you to make sure you are matching what are called your boundary conditions. For example, our time very likely is starting at time 0. You released the coffee filter at time 0. They want to know that you recognize this represents something physical. And they want to know if you can synchronize it. At time 0, what was the velocity?
0.
So on the velocity side, we want to make sure that we start with the same velocity that the object had at time 0. We are applying a boundary condition, telling our system where to start. Now, this next part, bear with me. This is what you need to do, and it might be confusing. But we're trying to build a function. Our function is going to some unknown time in the future. So the top time is t. Sometime in the future. I get the fact that there's a t here as well. They're not the same t. If that bothers you, then use a different symbol. Use a capital T. Now you have to link these together. So on the left side, We are looking for a function. This is going to be v as a function of t. We're going to some function with respect to t that tells me the velocity for all times in the future. So we are setting the top boundary. There's almost always a point associated with setting the limits correctly on your integral. All right. Now that we've done all that, your next job is to integrate this and get a solution. Now, just point this out. We've not done very much math yet, but we're on minute number 25 from the point where we started. And we've got just a couple of lines here. It's going to take 3 times the amount to get to the end. It's not because what you have to do now is harder. It's because there's an incredible amount of algebra to do. An incredible amount. The calculus is going to be 1 line. But if you don't know how to do the calculus, you can't do any of the rest. And here's an important detail. Although there's a lot of algebra to do, almost all of what happens next is only worth 1 point. So if they've given you the answer and you make it to here, you may want to skip that point and finish the problem. There's probably something else they're going to have you do with that function. They gave you the function for a reason. But if you want to know how to go to the next route, we're going to go to the next route. Now, I want to teach you how to actually do the math, but that's not going to happen today. Well, not in 2 minutes. First, the right side you're supposed to already know how to do because we've done it before. Do you remember how to do the right side? If you don't, remember there's a t there, a hidden t. It is t to the 0 power because there's a 1 there, an implied 1. And because it's a polynomial, t to the 0 power, I know that the antiderivative requires that I take t, add 1 to the exponent, and divide by the new exponent. That's how I deal with polynomials. The only difference is that I have to still apply my limits. The right side is not a polynomial. The right side is more complicated than that. And knowing that I'm out of time, allow me just to tell you that the answer, what you have to do next, is already given to you. It's given to you. That's why they don't give many points for this. You will be given from here. You should a set of these. Ignored every page but this one. Most of you have ignored. You shouldn't. There will be an integral table on your test. Let me start out by pointing out this is what we just did for t, right? We added 1 to the exponent and divided by the new exponent. I know they're using x. X is a placeholder. If I replace this with t, I would have gotten t to the 0 plus 1, 0 plus 1 in the denominator. That is the polynomial rule. Do you see anything here that looks like our function? It's this one. Now, we're going to learn how to use the integral table tomorrow, and we'll finish this.